Hello, in this video, we will delve into the topic of solving sequential circuits and explore effective implementation strategies. The video explored the intricacies of solving sequential circuits and offer insight into optimal implementation methods. Join us as we navigate through the key concepts and practical approaches to tackle this topic. Let's get started. Design a counter that displays odd numbers on a certain segments where the selector switch is on the off select position, and even numbers when the switch is on the on position.
Good day. I am Chad Vincent G. Filipino. I'm tasked to analyze the problem of this problem. The problem states that design a counter that displays odd numbers on a 7-segment display when the selector switch is in the off position, and even numbers when the switch is in the on position. Now, in a first analyzation, when selector switch is off, the display will be the odd numbers. The odd numbers, which are 1, 3, 5, 7, and 9 in a sequence. Second analyzation, when selector is on, the display will be an even numbers, which are 0, 2, 4, 6, 8 in a sequence. Next analyzation, according to the problem, therefore, these two analyzation, if we use multiplexer, the selector, if we use multiplexer for the selector switch, the flip-flop input will be the odd numbers or the even numbers. Even number. Next analyzation, the selector switch can be implemented using a multiplexer or MX. Next selector, since the MUX have two inputs, which are the odd number or the even number. So, towing siya. So, yun. Next analyzation, the selector line of the MUX will be connected to the selector switch. Kasi nga, there are two inputs. It will connect into the MUX, will connect to the reset. Last analyzation, we will be using it as a encoder to display the output on in 7-segment display. So we need 4 flip flops. To design the counter that displays odd numbers and to display the counter of the odd numbers on a 7-segment, odd numbers and even numbers on a 7-segment. That's all. Thank you.
So good afternoon, everybody, and now let's proceed to the state diagram. As what it was stated a while ago, in this problem, we're going to display an odd number in the 7-segment display when we turn off the switch. And we will going to display also the odd numbers when we turn on the switch. And as we can see here in our state diagram, this circle represents the states, while here this arrow that has a 1 value, all that has a 1 value represent the on switch, while this arrow that has a 0 value represent the off switch, which wherein when we try to turn off the switch, it will display the odd numbers, and when we turn on the switch, it will display the even numbers. And this is how our state diagram works, wherein when we try to start in the one state, when we try to turn it on, when we try to turn it on, it will, since turn on switch will display an even number, it will redirect it to the state value of 2, 4, 6, 8, and back to 0. Then when we try to turn it off the switch, it will be redirected to the display number of 1, 3, 5, 7, 9, and back to 1. And that's how our state diagram works. And now let's proceed to our state table. And as we can see here in our state table, we created there that decimal display, which will represent all the output of the 7-segment display. Then we have a selector, which has a turn off, which has a value of 0, and turn on, which has a value of 1, then the present state and next state. And as we can see here, when we try to select 0, which is when we try to turn off the switch, it will display the odd numbers that has a value of 3, 5, 7, and 9. Right, in the present state, when we turn off the selector, it will display the value of 1 in a binary numbers. Then in the next state, it will turn into 3, and when we try also to put here the selector in the present state that has a value of 3, its next state will be 5. Then in the present state of 5, the present state of 5, it will be, since that we use turn off selector, it will be redirected to the next state that has a value of 7, and so on and so forth. Then when we try to turn on the switch in 0, then it will the present state will display 0 in a binary number. Then when we try to turn it on, on the next state, it will display here the binary number of 2. Then the 2 here, it will be copy here the binary number. Then the next state will be 4, and so on and so. And this is how we presented the state table of our problem.
So, good. Thank you, Miss Pamela. So, the next is about excitation table using deepen. So, first, the excitation table of deepen is where, as we observed, it the same when the next state is 1, the D is 1. When the next state is 0, the D is 0. So the develop inputs of deep flip-flop is the same with the next state. So we can just copy the next state to the flip-flop inputs. So next is for key mapping. For key mapping, we assume the don't care as 1. So first, we need to separate the key mapping for odd numbers and even numbers. First, odd numbers. Key mapping for input flip-flop equation of odd numbers. So E3 D3 muna. So D3 is 0 0 0 1 0. So it can high only when the present state is 0 1 1. So 0 1 1 1. So 8 7. So 0 0 1 1 1. So high. So a day 0 0 0, and the rest is don't care. So we group this for 0 1 E2 and then E1. So E2 and E1 for D3 of odd number. Next is D2. D2 is 0 1 1 0 0. So it's high when the present state is 0 0 1 1 and then 0 1 0 1. So 3 and 5. 3 0 1 2 3 4 5 1 1 0 0 0. So don't care, and the rest is don't care. So group this E2 and then E1 plus another group is A2 prime and then E1 prime. So next is D1. D1, it only high when the present state is 1 and when the present state is 5. So 0 1 2 3 1 4 5. So 1 and 5. So this is group 0 E3 and then E1. Next is D0. D0, as you observe, it 1. All the combination of odd is 1. So we can just 1 1 1 1 1, and then we assume the don't care as 1. So D0 is equal to 1 or VCC. For even numbers, for D3, the one on the D3 I only when the present state is 6. So 0, 1, 2, 3, 4, 5, 6, 6. So group this and then E3, E1. And then this is on low also E2. So 0, 1, 2, 2, 3. So 2, 3, 4. So 2, 4. It only I. So group this, group this. So it's the same. So also this one and this one is, as we observed in the excitation table, when the selector is 1 or on a person, the D0 is 0. So 0, 0, 0, and then D0 is 0. So in summary, the input flip-flop equations for odd numbers or when the selector is equal to 0, E3 is equal to E2, E1, D2 is equal to E2, E1 prime plus E2 prime, E1. D1 is equal to E3 prime, E2 prime. D0 is equal to 1 or VCC. For even numbers, selector is equal to 1, D3 is equal to E2, E1, D2 is equal to E2, E1 prime plus E2 prime, E1, D1 is equal to E3 prime, E1 prime, D0 is equal to 0 or ground. So, we observe that D3 and D3, D2, D1, D3, D2, D1 for both even and odd numbers are the same, while D0 is complement value for the selector. For odd numbers, when the selector is 0, D0 is equal to 1. Similarly, for even numbers, when the selector is 1, D0 is equal to 0. Therefore, there is no need to use multiplexer or MUX. We can simply connect the output for D3, D2, and D1 and connect the inverted selector switch to D0. So this is only the input flip-flop equation, and that's all. Thank you.
I'm Adrian. So after Clement, they have shown us about the excitation table and key mapping the flip-flop inputs. Can we visualize the whole problem with those schemed up solutions? Aha, a diagram. But what kind of diagram? You're in luck. So in this video, we'll be doing that by creating this diagram or so. And let's just dive in and use CircuitVerse as our digital circuit simulator. Correct flip-flop implementation in a circuit is crucial for accuracy, synchronization, and memory. Here is the reasons why. Flip-flops as binary devices are crucial in binary systems for accuracy, synchronization, and memory. They are essential for implementing counters, ensuring accurate outputs. They synchronize operation within a circuit like coordinating as a counter and a 7-segment display. Lastly, they store binary digits, providing memory for system that needs to be remembered. In conclusion, the correct implementation of flip-flops is vital for the accurate and reliable operation of digital circuits, whether it's counting odd or even numbers on a 7-segment display or any other digital tasks. Flip-flops are the building blocks that make it possible.